Welcome to Ready to Derive. In this video, we're going to be exploring inverse functions. Now, we're very familiar with inverse functions. We use them all the time. Take -5, multiply it by 2, and you get -10. And the inverse of that would be, obviously, to divide by 2. What about something a little more complex? If you take 4 and cube it, then you would get 64. And the inverse of that, to get back from 64 to 4, would be to take the cube root. We even have some pi over 2 we're familiar with. If you take the sine of pi over 2, you get out 0.5. Now, to get back, we can't actually physically do that in our minds. We either have to know the result or we have to use a calculator with that special inverse function. So you've actually seen inverse notation, sine to the -1. So we are going to be exploring this in much more depth. We're going to be stringing functions together, individual functions. So for example, if it was the sine of 2x cubed, how would you find the inverse of a more complicated function? We're exploring lots of fun properties, algebraic and graphical. And so without further ado, let's begin. So let's look at a little notation and fun facts associated with a function and its inverse. So let's take the simple function, the f of x equals 2 times x. So we know that, for example, -5 would map it to -10, 0 would go to 0, 1 to 2, and say 3 will go to 6. So clearly the inverse function has to kind of undo that process. So let's use a different color. So for example, so to get back from the right-hand side to the left, that would be the inverse function. We have special notation for that. We write f to the -1 of x, as opposed to just calling it a new function like g of x, because then we wouldn't realize how intimately connected they are. So in this case, we see that the inverse function, we would take the values on the right-hand side, like -10, and have it to get 5. So the inverse function would be this, same for 0 to 0, 2 to 1, and 6 to 3. Now, let's recall some other terminology for functions. So for example, for f of x, this is considered the domain, the values on the left, and these values on the right would be the range. Notice that for the inverse function, that is reversed. So as far as the inverse function is concerned, the values on the right are its domain. So that's fact number 2, very important one. The domain and range of a function and its inverse are reversed. And here's another important fact. It sort of seems obvious, but it's kind of essential understanding, is that if we have f of a equals b, so for example, f of 3 equals 6 for our function, then it follows, sort of obviously, that the inverse function applied to that output of 6 must get you back to the original. Okay, so notice that what we haven't got in this mapping of a function I've shown is we haven't got the situation where, say, 4 also brings you to 6. And that really sort of situation complicates the concept of an inverse function, because if you think about it, if also f of 4 gives you 6, then which value, to be a function, when I put 6 back into the inverse, am I going to get out 3 or I'm going to get out 4? We'll treat that later in the video, but for now you have the most important essentials of a function and its inverse. So we're going to dive right in and try to find the inverse of a more complicated function. So 2 times the square root of x plus 3. More going on here, as I'm not even teaching you how to find the inverse yet. We're going to do this kind of intuitively. And to do so, let's just pick a number. Let's just find what f of 16 is. So f of 16, we would plug 16 in for x, and we would do rad 16 is 4. 2 times 4 is 8, and 8 plus 3 is 11. So knowing the properties, as we have just learned, property number 3, we know that when we've constructed the inverse, then it should take 11. If you put 11 into it, it should get you back to 16. So let's see if we can make that happen. So I'm going to do this using diagrams as I did on the introductory slide. So let's take our input of 16, and we're going to think about f of x. So f of x, the first thing it says to do is to take the square root. So square root of 16 is 4, and then multiply by 2 to get 8, and then add 3 to get 11. So f of x is basically taking us in this direction. And we need the inverse function to reverse that. So the last thing we did was add 3. So to get back from 11 to 8, we have to do the inverse of that, which is subtracting 3. To get from 8 to 4, the inverse of multiplying by 2 is dividing by 2. And the inverse of square rooting is squaring. And so this is going to be f to the minus 1x going in that direction. And if we think about it then, so let's try and just create this function. So this says take whatever the input is, right? So the input here was 11, but let's just call that x instead. Whatever the input is, x, the first thing we do is subtract 3, then we divide by 2, and then we square the answer. So let's see how we did. Maybe I'll just go back to white for now, just to make it a little easier to read. So let's check. If we put 11 into here, so 11 minus 3 over 2 squared, 11 minus 3 is 8. 8 over 2 squared, 8 over 2 is 4. 4 squared is 16. And check, that matches what we wanted to do. And there we have it. We created the inverse function by reversing the steps of the original function. Okay, so now rather than make that type of diagram every time we have a problem like this, in the next slide I'm going to teach you an algorithm, a method for finding the inverse. So now we're going to go through the steps of an algebraic method finding an inverse that works every time. So no matter how complicated the function. So we'll use the same function that we did in the previous slide. And the first step is to replace f of x with y. So y equals 2 rad x plus 3. And the second step is to switch x and y. The very act of switching x and y actually creates the inverse. So if we think about it, on y equals 2 rad x plus 3, if we were to graph that, we know that the point 16, comma 11 is on that, because when we plug in x equals 16, we get y equals 11. So on the inverse function, we need to switch those positions. We need to, that when we plug in 11 as x, we get 16 as y. So that's on the original, and this is on the inverse. So we do that kind of just generically by switching x and y, switching the outputs and inputs, and then solving for y. That's our next step. So solving for y. So if we want to get y alone, the first thing we have to do is subtract 3. That should sound familiar. That's what we did in the previous slide. We get x minus 3 equals 2 rad y. Next step, divide by 2 on both sides. So we get rad y equals x minus 3 over 2. And the final step would be to square both sides. And of course, rad y squared, that will get y alone. And then we have the inverse function. Actually, we had the inverse function at step 2. The minute we switch x and y, we had created the inverse function, but we like to kind of solve for y, isolate y, so that we can replace y with the proper notation, and our inverse function is as we obtained before. So we'll practice this again in the next slide. So for this practice problem, we are going to find the inverse of this cubic function. So the first step is just to replace f of x with y, as said before. And the second step is to switch x and y. So I'll do that right here. And then we just solve for y. So first step, subtract 3. So x minus 3 equals half of y minus 1 cubed. Then I would multiply up by the 2. So we could distribute that, or I could just leave that as 2 times x minus 3 equals y minus 1 cubed. Next step would be to take the cube root in order to undo the cube. So cube root of 2 times x minus 3 equals y minus 1. And finally, the last step would be to add 1. I'm going to just kind of rearrange that now. So we have cube root of 2x minus 3 plus 1. Oh, I said that's the last step, but actually the very last step, rather than write it all out again, is just to replace that with f to the minus 1x. Okay, so that's our inverse function. The steps are pretty straightforward and easy to follow. I just want us to have a little look at the visual because there's another kind of property of inverses, graphical property, which is interesting. So here we have, so the green function is the original, f of x. And then if I graph the inverse, which is a cube root function, it actually looks like this. And you will notice, okay, that's an orange. They have a very important symmetry, and that is across the line y equals x. So a function and its inverse will be symmetric to the line y equals x. That's the dotted line there. So that's an important fact. You might want to note that down. And there's another, the other fact that I want to revisit. So fact number 3, you will notice that take a point on the original function. So that is a point 1, 3. And you will notice that on the inverse function, that's 3, 1, the same point, those x and y's switched. Now, I know we've said that in different various ways, but let me formalize that. So if the point A, B is on F, it follows that B, A is on the inverse function. And we saw this before, but we wrote it like this. So if f of A equals B, then, of course, f to the minus 1 of B equals A. It's just nice to kind of see it rewritten in terms of coordinates of points. So here's another practice problem. This one's a little more intricate, so let's run through the steps. So first step, replace f of x with y, and then switch x and y. So we'll just go straight to that step. And now what you're going to notice, so if we cross multiply, think of this as x over 1, and we cross multiply, we would get x times y plus 3 in parentheses equals 2y. Now notice that we have y in 2 different locations, so it's a little harder to isolate y this time. And the way we're going to have to do it is first we'll kind of break it out of its parentheses here by distributing. And then we are going to have to assemble the y terms on one side. So let's subtract xy from both sides, and we get this. Now, there's only one way to sort of isolate y in this case, and it's to realize that you can actually just factor it out. So if I factor y out of the parentheses, I'm left with 2 minus x. Rearranging, I get y equals 3x over 2 minus x. And of course, I can go in and replace that with the inverse function notation. So that is our inverse function. Now, in terms of finding the domain and range, we really have to remember a very important fact. The domain and range of a function and its inverse are reversed. So, and that's going to help us here because, all right, let me call up this table. It's going to help us here because if we think about, and I think I'll use different colors here. Okay, let's go to the original function. If we think about this, the domain, we just can't divide by 0. So we know that x cannot be equal to -3. So I could actually put that in here. You could write it in interval notation, or if you know set builder notation, it's a little more expedient. So you would say x is not equal to -3. Now it turns out because the domain and range are reversed, we can then automatically, we know that this is going to be the range of the inverse function. So at this point we have to switch x and y and make sure that y is not equal to -3. Okay, but now what about the range of this function? So if we think about the range, well, that's actually the range of this function, the original function, is a little hard to know unless you've like dealt with rational functions before. So if you know the trick, it's manageable, but otherwise it's really hard to predict what y value cannot come out of that function. We can't consider all the possible x's and whether there's one y value that might not be allowed. But now we use the fact that the domain and range are reversed. And what we do is we kind of cheat a little and we come to the inverse function and we say, well, what's the domain of the inverse function? Well, the denominator can't be 0 again, so x cannot be equal to 2. And when we realize that that's the domain of the inverse function, so x is contained in the set of real numbers such that x is not allowed to equal 2, then we can steal that and use that for the range of the original function. Remember, it was a little hard to tell what was allowed or not allowed to come out of this function, but now we know that y is contained in the set of real numbers and y is not going to ever be equal to 2. There's no value of x that would generate a y value of 2 in that original function. So now we need to look at some complications that arise when dealing with inverses. So let's start by graphing the function f. And we know that one of the properties is that you can create the inverse by reflecting over the line y equals x. But we run into a little bit of a problem. All's good and well right now, but what if this function f, what if it kind of went back up, kind of like a parabola? Then if we continue to graph the inverse, the reflection, it would go like this, and it would no longer be a function. I alluded to this on the intro slide when I said, for example, if one, say in the domain, 1 maps to the element 2. So that could be, like, say this point is 1, 2. But say also that -3 maps to 2 also. So for example, this point is -3 mapping to 2. Well, then we have a real problem, because if we put 2 into the inverse function, we don't know whether it's going to yield 2, 1 or 2, -3, and we have a problem. So the problem is for a function to have an inverse, it must be what mathematicians call a one-to-one function. And what is a one-to-one function? It's that each element in the domain maps to a unique element in the range. So in other words, if 1 goes to 2, then we can't have -3 going to 2 as well. So how do we compensate for that? So when a function is not one-to-one, we must restrict its domain. In fact, what we say is a real good quick test to see if it has an inverse or not is to make sure it passes the horizontal line test, which means a horizontal line can't intersect the function more than once, which it does up here. Now, how do we compensate? How do we restrict its domain? Well, we make sure that it's one-to-one. And so, for example, if I didn't allow that function f to go beyond that point, then notice that its inverse would be a function. So we are going to practice restricting the domain of a function so that its inverse exists. So let's practice a problem where we will need a domain restriction. And this function f of x, if it was just a standalone problem and it asked for the domain, we'd say, well, it's all real numbers except 5, because you can't divide by 0. But there may be more to the restrictions in domain than that, and I can sense that there might be a problem, because if you, let's see, if you work out f of 6, you can do that right now, you'll get 2, but you'll also get 2 if you were to put 4 in, because 4 minus 5 squared and 6 minus 5 squared, they both work out to be 1. So we know that there's going to be a little bit of an issue, but it might be hard to predict how to restrict that domain just yet. And one way to be certain is to actually find the inverse function, and you can learn a lot from that. So let's find the inverse. So let's begin by switching x and y. And then I'm going to bring the 1 over y minus 5 squared term to this side, so it becomes positive, and then 3 minus x over here. I'm going to put that over 1. Because I want y in the numerator, I'm just going to take the reciprocal of both sides. So I get this. At this point, the inverse operation of squaring is square rooting. And you should know that, of course, when you take the square root, there can be the positive or negative version, but we know that will result in something that's not a function. So it's customary to take the positive square root. But we make a choice in doing that. We could just stick with the negative square root, but and that would influence the domain restriction in a different way. We'll see that visually in a moment. Now the square root of 1 is 1, and then we have the square root of 3 minus x. And now if we just add 5 to both sides, we get this. And of course, I can come in now, take that y away, and call this the inverse function. So as I look at that inverse function, the domain that pops out right easily, because 3 minus x, not only can it not be 0, but it must be greater than 0, which means that x is less than 3. So we already have some information that can help us. So the domain of the inverse function will have to be, now I'm going to use interval notation just to change it up, will be negative infinity to 3. And then we know that we can borrow that, and that will be the range of the original function, which is not something we might have noticed at first. But if you think about it, you're going to always be doing up here, you're going to always be doing 3 minus some quantity, some positive quantity. So that means the answer is always going to be under 3. Okay, so now in terms of thinking about the domain of f, actually, let's just think about the domain of, the range of the inverse function. So notice that the inverse function starts with 5 and then always adds a positive quantity to that 5. So it's impossible to get 5 out as the output, but it is possible to get anything above 5. And so that tells us that we can use that information to find that this is 5 to infinity, and there we go. There is our domain restriction for the original function, because we have to match that. And that means that if x can only be above 5, then f of 4, that's disallowed, which kind of makes sense. And let's just look at that visually. Let's look at the situation. So here's the original function, and notice it fails the horizontal line test, as we predicted. And if we reflect that over the line y equals x, we see, of course, we have something that is not a function, the orange one. But then we go and restrict the domain, and so we only allow x is greater than 5 in the original, the green function, and we get this, and perfectly well defined, and domain and ranges very clear. So we're going to end by looking at a very important test to determine if two functions are inverses. It's more than just a test, it's also a very important property. Sometimes it's even considered the definition of what inverses are. So let f and g be two one-to-one functions. And if the composition of f and g, or g and sorry, not just or, and g and f, in both cases, if that yields x, then we know that these are inverse functions. And let's just remind ourselves of what the composition of functions means. So this means find g of x, plug that into the function f, and it should yield x. And we know that about inverse functions, right? For example, if you take 5 and you square it and you get 25, then when you go back, you take the square root, you get back to the original value. So this is just another way of writing something we already know. And let's just demonstrate that for a simple scenario. So suppose you know that f of 5 equals 2. Then, technically, the inverse should take 2 back to 5. So let's look at the composition in both directions. So f of g of whatever you put in has to generate that answer. So x has to give x. So if we go, but let's see, the only thing we know about is we know g of 2. So let's put in 2 here. And if we find g of 2 is 5, and then if we plug 5 into f, we know we get 2. Check, that works. Let's look at g of f of, well, the only thing we know for right now is what f of 5 is. So f of 5 is 2, and g of 2 is 5, and that checks. So we'll end by just practicing a couple of examples of identifying if functions are inverses of one another. So this is the very last practice problem. We're going to determine if f and g are inverse functions, and for simplicity of viewing, I'm going to color code this. So we're going to start by looking at f of g of x. So f says whatever you put into me, take a third of that and subtract 5. And then we come along and we want to see, well, let's just put the whole of g of x in there. So g of x is 3x plus 5. Just go to, and then what we do is simplify. So we'll distribute and we get just x plus 5/3 minus 5. Oh dear. So it just seems like they don't cancel out to give x, and therefore we don't even have to check g of f of x. We know that these are not inverse functions. If one of them fails, it's no point checking the other. And for the next practice problem, we're going to take the function and the inverse we determined earlier and just kind of verify that it works. So f says, whatever you put into me, double it, that quantity, and then divide by that quantity plus 3. And we go and put in the whole of g of x. So that's 3x over 2 minus x, 3x over 2 minus x. And with a complex fraction like this, it's easier just to wipe out the denominators by multiplying the top by 2 minus x over 2 minus x. That will cancel to leave us 6x on the top. And we have to be careful here when we distribute. The 2 minus x will certainly cancel with that 2 minus x, but it's also got to multiply by the 3. So we get 3x plus 3 times 2 minus x. So 6x over 3x plus 6 minus 3x. The 3x's cancel, and the 6's cancel, and we are left with x. So that checks. F of g of x delivers x, and I'll leave that up to you, the viewer, to check that g of f of x also yields x. Thank you for sticking around to the very end of the video. If you enjoyed it, found it useful, please do like the video and subscribe to my channel, Ready to Derive, and check out some of my other videos.